Hi, my name is Chase, and welcome to another edition of Chem Rocks 123. In today's lesson, we're going to focus on chair conformations of cyclohexanes and look at how we can best stabilize these structures. Shown here, we have a cyclohexane. A cyclohexane is a ring with 6 carbon atoms, also known as a cycloalkane. This two-dimensional figure is one way to draw this molecule. However, we can also represent a cyclohexane with a chair conformation. Now, in order to understand and create a more stable configuration, we need to address 2 different positions, axial and equatorial. Let's begin our lesson here. Shown here is a chair configuration of a cyclohexane. Okay, so we will start here with the uppermost carbon and we will label it as carbon 1. We do this to help us stay organized when we begin to add our axial and equatorial substituents. It does not matter which carbon you label as the first one, as long as you make sure to keep going in the order that follows. So, you will see here that this is carbon 1, the next one is carbon 2, and the next one carbon 3, and so on and so forth until you've counted all 6 carbons. Let's start by adding the axial substituents first. We will use red to represent them. As you will begin to notice as we start labeling our cyclohexane, the axial positions are faced either upwards or downwards, and the equatorial positions are located out towards the side. Starting with the first carbon, we will begin by adding the first axial position in an upwards direction. The next one, on carbon 2, will be facing in the downward direction. The next one will go up again, and then down, and then up, and then down. It's going to alternate positions in that same pattern. Using blue, we will add our equatorial positions to our cyclohexane. Now, since the axial position on the first carbon is in the upwards position, the equatorial one will be facing downwards. In this pattern, like we saw with the axial positions, will alternate as well. As we see for carbon 2, we have a downward facing axial, so our equatorial must be, yes, as you could have guessed, facing upwards. We will repeat this pattern for the rest of our chair configuration until, voila, we have added all of our axial and equatorial positions. As you will notice, we have 6 equatorial positions and 6 axial positions. This is what our chair configurations for cyclohexanes look like. Now that we know this, let's look at a chair configuration with different substituents and learn how we can arrange them into their most stable form. We will look at an example here with a methyl group attached as a substituent to demonstrate how having a larger substituent in the equatorial position is a much more stable configuration than if it were in the axial position. This methyl group is located in the axial position. As you can clearly see, there is significant steric strain between carbon 3 and carbon 5. This largely destabilizes the configuration. However, as we move over to our next cyclohexane, which has a methyl group in an equatorial position, we can see that there is negligible steric strain present. This creates a chair conformation that is much more stable, lower in energy, and heavenly favors the right side. On this chart here, we have 4 different substituents. As you will notice, as we move down the chart, the substituent size increases. In order to help you recognize and learn this topic, we have drawn different box sizes for the different substituents. This provides an easy way to visualize and remember that these substituents differ in size. As you go down this column, the size of the attached molecules increases, as too do the boxes that they are written in. As we go across the chart, we will see percentage favored for axial versus percentage favored for equatorial. This demonstrates which position will yield a more stable configuration. Clearly, as the substituent gets larger, the cyclohexane begins to favor the substituent more. Starting with the methyl group, which only favors equatorial 60%, compared with the largest molecule in this chart, which favors the equatorial position more than 99.99%. Overall, the trend is clear. The larger the substituent is, the more likely the chair conformation is to favor an equatorial position. I hope this video was helpful for you. Tune in next week for another episode of Chem Rocks 123 with your host, Chase.